Hey everyone, welcome back to linear algebra. This will be part B of lecture 12, and where we left off we had just defined eigenvalues and eigenvectors. We've defined eigenvalues and eigenvectors, how to find each of them. Okay, so that's what we talked about. That's where we ended part A, right? So it seems like we didn't maybe too much, but we did a ton actually. Those are eigenvalues are tricky ideas. And so what we want to do next is we want to move into a discussion of diagonalization. Okay, so we want to move into diagonalization. And so really one of the most important uses of eigenvalues and vectors is in the diagonalization of a matrix, right? So probably the most, I mean, if you can say such things, what's the most important? The most important, uses of eigenvalues / vectors is in this topic. Maybe I should say one of the most important uses. Right. So, and so let's start, rather than just racing off with a definition. Let's try to generate, let's kind of create a motivating example here, just to kind of give some sense of what the point of it is first, because it can be a little bit tricky. Right. So a motivating example. Okay, so let's say we have A, and we'll reuse the A from our previous sections, from our previous examples. -4, 8, -12, 6, -6, 12, 6, -8, 14. Okay, so we've got this familiar 3x3 matrix. Now we saw earlier that this matrix had two eigenvalues. Has two eigenvalues, right? So the first one we said was λ1 equals 2, and the second one was λ2 equals 0. And we found eigenvectors to go along with these, right? So let's say we had x11, that one was the 4, 3, 0, and x 1, 2, we'll say, which was -2, 0, 1. Now these both correspond to λ1 equals 2. So this particular eigenvalue has two distinct eigenvector families here, right? So both of these can be, you can spin up infinite variety of versions of x11 and of x12, but these two are incompatible, right? One is not a scalar multiple of the other. Okay, so we had these two for λ1, and then for λ2, we'll say x2, the vector x2, which is -1, 1, and 0, and this one is for λ2. Okay, all right, there we go. Right, and so this is kind of like what we figured out previously, so we're going to reuse this information because it's familiar and we don't have to conjure things out of totally thin air. Okay. All right, and so what we're going to do is we're going to build a matrix, P. We're going to call it the P matrix. And P is going to be basically, it's going to have, the columns of P are going to consist of the eigenvectors that we have discovered. Now, ideally, every eigenvector will have at least one, every eigenvalue will have at least one eigenvector. In the case of λ1 equals 2, it's going to have two eigenvectors, right? But every eigenvalue needs to have at least one eigenvector in this matrix P. And so our matrix P is going to be x11, x12. Those are the two eigenvectors corresponding to λ1. Those are going to be the columns, the first two columns of P. And then the last column is going to be x2. All right. So remember, these are the two for lambda 1 that correspond to lambda 1, and this one is lambda 2's eigenvector. All right, so the order here is going to matter in what's to come. So just keep straight that lambda 1's come first, and then lambda 2's are the second. All right, and so let's go ahead and put those in. So we'll have 4, 3, 0, negative 2, 0, 1, negative 1, 1, and 0. Okay, so this is what we're going to call our P matrix. Okay. Now we can calculate the determinant of P if we want to. And if we do that, we'll see that the determinant is negative 1. The determinant isn't important for what's to follow, but what is important is that P be non-singular, right? So P has a determinant of negative 1, and that's going to imply P is non-singular. Now what does that further imply? P inverse exists, right? We need the inverse of P to exist in order for this to work. Okay. All right. So we've got our P matrix, where basically the columns have been built up based on the eigenvectors, and we've determined that P has an inverse. And in our case, we didn't find the inverse yet, but we just determined that it exists, and that being identified through the value of the determinant. Okay. Now, so what we can do is, there's several ways to identify the inverse of a matrix, some of which we've talked about, but we do need the inverse now, right? And so you could just use row reduction. To find the inverse, whatever method you want to use to find the inverse, row reduction is probably the most efficient. But we do need the inverse, and the inverse turns out to be 1, negative 1, 2, 3, negative 4, 7, and negative 3, 4, negative 6, right? So this is the inverse of P. Okay, so we've got our P matrix, and we've got our inverse P matrix. Okay, so what we can do is we can now use A, P, and P inverse to compute a diagonal matrix. Okay, and that's what we're going to do. So once we've identified our eigenvalue and vectors, we can construct P easily, calculate the inverse of P right here, and then we can use P and P inverse to do what's called diagonalizing A. Okay, and so our diagonal matrix is going to look like this. D for diagonal, it's going to be equal to P inverse times A times P. Okay, now if you do this exercise, I highly encourage you to do it. Let's go ahead and write it all out. So P inverse, we found 1, negative 1, 2, 3, negative 4, 7, and 3, 4, negative 6. A was our original matrix, negative 4, 8, negative 12, 6, negative 6, 12, and 6, negative 8, 14. There's our A. And then P is 4, negative 2, 1, 3, 0, 1, and then 0, 1, 1. And again, these are the eigenvectors. And when you multiply these three together, you get a diagonal matrix 2, 0, 0, 0, 2, 0, 0, 0, 0. Now, what about this diagonal matrix jumps out at you? Well, the main entries of the diagonal matrix are the eigenvalues of A. The main entries of D on the diagonal are the eigenvalues of A. Okay. Now, notice also that the corresponding columns of P are the eigenvectors of A. right? So this guy here goes with the eigenvalue 2. This guy here also goes with the eigenvalue of 2. I think this is supposed to be -1. And this third eigenvector in P corresponds to the eigenvalue of 0, right? So you've got your eigenvalues on the diagonal. And the eigenvectors, however you've organized them inside of P, it will spit out a diagonal matrix where the corresponding eigenvalues are in the same alignment. Fascinating. That's amazing, right? So you build a matrix out of your eigenvectors, identify the inverse, and do this calculation, and what gets spit out is a diagonal matrix with the eigenvalues in it. Okay, so there's obviously this very deep connection here. Okay, so let's go ahead and formally define this diagonalization. Well, it's not actually a definition, it's a theorem. Let's go ahead and lay it out, though. Let A and P be n by n matrices. Let A and P be n by n matrices such that each column of P, so each column of P is an eigenvector for A. Okay. If P is non-singular, then D equals P inverse AP is a diagonal matrix It's a diagonal matrix with its ith main diagonal entry ith main diagonal entry DII equal to the eigenvalue for the eigenvector that's in the ith column of P. So DII is equal to the eigenvalue for the eigenvector in the ith column of P. Fascinating. Brilliant. Okay. Now, you may think that the proof of this is beyond us. This seems very deep. This seems incredibly deep. But we can pretty well sketch the proof out here in just a couple of minutes. And so let's do that. This won't be perfectly rigorous, and maybe some details could be filled in, but let's just go through kind of the rough sketch here. So let's let P be the matrix we've defined, right? So the matrix as we've set up, whose columns are the eigenvectors of A. Okay, so I've got, basically what we drew, V1, V2, ... Vn, right, where the VI's are eigenvectors. I better write that, where VI are the eigenvectors. Okay. Now, so this is P. So we're calling eigenvectors are being denoted with V, and P is built up of columns of eigenvectors. Okay, and so we know, just by definition, we know that A times V1 equals lambda 1 times V1, and A times V2 is equal to lambda 2 times V2, ... A times Vn equals lambda Vn. What is this? Well, this is just the definition of eigenvalue eigenvector, right? This is just the definition. So we know if Vi are our eigenvectors and lambda I is our eigenvalues, and when they correspond, their indices correspond, then this relationship holds. So let's consider the product AP. So the matrix A times this matrix P, which is comprised of columns of eigenvectors. So AP is equal to A times V1 dot 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 Vn, right? Okay, these are columns in a matrix. And we know that that's equal to the matrix that would look like this: lambda 1 V1 dot 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 lambda n Vn. Right? This just follows, right, directly from what we previously stated. Let's multiply both sides of this expression by P inverse. Right? So AP times P inverse will be equal to lambda 1 V1 dot 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 lambda n Vn times P inverse. Right? It's just multiplying both sides by the inverse of P, which we assume exists. Okay, I should write that down. So multiply both sides by P inverse, which exists by assumption. Okay. And so we get this. And let's consider the product lambda 1 V1. Right, so you've got this thing here. So consider the product lambda 1 V1. Right? This is a matrix, right? This is a matrix where everything in the matrix is multiplied by lambda. So clearly, it is possible to represent this as follows. This can be represented you can clearly represent this as V1 times V2, these are columns, dot 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 Vn times some other matrix, lambda 1, 0, 0, dot 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 0, 0, lambda 2, 0, dot 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 0, 0, 0, lambda 3, dot dot dot. So I should have, right? And so all the way down to lambda n, right? So some other matrix where basically everything is 0, right? Everything off diagonal is 0. Well, what are these? Right. So just check this. Check to make sure that this is true. Right. Confirm this on your own. Take your matrix that consists of all the eigenvectors, and take a identity times lambda. Multiply these together, and you'll see you get exactly this. Well, this is just P times D, isn't it? Right. This is the diagonal matrix that we're looking for. This is P, what we started with. Right? And so up here, this is just P times D. And so let's bring that down here. So what do I have? I have AP P inverse equals lambda 1 V1 dot 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 lambda n Vn times P inverse. Well, what is on the left-hand side here? Well, this is A times the identity, isn't it? Right? And so A times the identity is equal to this. And you could just drop the identity matrix, couldn't you? And say this is A. Now what is this? We just showed that this can be represented as P times D. This has to be P times D. Right? And so that's exactly what we're after. Right? And so that is the result. Right, now again, there are some subtle nuances here that could be fleshed out a little tighter, but this is a sketch of the proof. This is a deep theorem from linear algebra. This is a very relatively easy thing to prove, given how deep it seems to be. Okay, perfect. So now we've seen a proof. We kind of see how this diagonal matrix can be or well, what it's all about. We can kind of see some of the inner workings. This has to do obviously with the nature of eigenvalues and vectors, has to do with the nature of multiplication of matrices, inverses, etc. So it pulls a lot of things together. You can kind of see the mechanism here. How can we go about performing a diagonalization in practice? Like, what is the approach? So the general method for diagonalizing A. Right, so this is maybe not going to be pretty, but it works. Right. So the first thing we got to do is calculate the characteristic polynomial. We need to know the eigenvalues. Right, and so that's x times the identity minus A. So we start with that, and this is to identify the eigenvalues. Step 2 then is to find the eigenvalues, so find all the real roots. Okay. Right, so find all the real roots. These are the eigenvalues of A. Okay. Step 3 then, we need the eigenvectors. Find the eigenvectors. So this is you'll have to iterate, right? You'll have to go, eigenvalue by eigenvalue, but for each, for each lambda I, what do we need to do? We need to row reduce. We need to row reduce this system, lambda I times the identity minus A equals 0. Right, so this homogeneous system. Okay, use, and then, use the result to find as many solutions as possible. Okay, so use the result to find as many solutions as possible, and I'll just put to lambda I minus A equals 0. That system. All right, and those are going to give you your eigenvectors. Right, and so that's where you're going to spend a lot of time, right? So after you do step 3 a number of times, you're going to spin up a number of eigenvectors. Now, if the number of distinct eigenvectors is less than n, quit, give up, walk away. You can't diagonalize A. And that can happen. Right, because if the number of eigenvalues are less than n, you can't even form P without using scalar multiples of one another. Right, and if you use scalar multiples of one another, then the matrix P will not be full rank. It will not have an inverse, so you can't diagonalize without an inverse P. Okay, so if you get to 4 and you don't have enough eigenvalues, you have n minus 1 eigenvalues, you can safely walk away and say, I can't diagonalize this. There's not enough eigenvalues. P will not be invertible. Okay, but assuming that's not true, form the matrix P. All right, so you can form the matrix P whose columns are eigenvectors, and then you're done. At that point, you're done. So verify that D is equal to P inverse AP. Basically, you've got P inverse, you've got A, multiply them together, you got D, which should be the diagonal matrix that you're seeking, which should consist of a diagonal matrix with eigenvalues on the main diagonal. Okay? Simple, right? Well, yes and no. I mean, it's not the most, it's relatively straightforward. I mean, if you're comfortable with all of these concepts of of solving systems, of finding determinants, etc. Like if you're comfortable with all of that, this is not impossible, but it can be computationally involved. It can be very computationally involved depending on the matrix. Okay, and so we're going to actually do an example here, and I'm going to fill in a lot of things from my example. I'm pulling this example out of a textbook, and the textbook isn't going to provide examples, and I'm not going to provide the textbook isn't providing the calculations, and I'm not going to either. I'm just going to present them to you, and you can verify them. But this will help you at least see the process at work here. So let's let A be a 4x4 matrix. So -4, 7, 1, 4, and then 6, -16, -3, -9, and 12, -27, -4, -15, and then -18, 43, 7, and 24. Okay, so here's our matrix. So, okay, so that's our 4x4 matrix. And so step 1 is to calculate the characteristic polynomial, right? And this is a lengthy computation. So the characteristic polynomial is found by basically identifying the determinant of this matrix, xi minus a. And so this will be a 4th degree polynomial. It turns out it's equal to x to the 4th minus 3x squared minus 2x. And that can be factored down into x times x minus 2 times x plus 1 squared. Okay, so that's step 1, is to find that characteristic polynomial. Now this is a chore, right? This is a real chore here, because you're going to have to calculate the determinant of this 4x4. It's certainly doable, but it is not something, it might take you a half an hour to do that part. And I recommend you do it though. Just do it once so you can make sure that you see how end to end there is no trick, there's no gimmick here. This really does indeed work. Okay, so try that. Step 2 then is to set this polynomial, the characteristic polynomial, equal to 0 and solve it. So PA of x equals 0. And when you do that, you get 3 eigenvalues, right? So you can see what they are. I mean, you're going to have lambda 1 is going to be -1, lambda 2 we're going to call 2, and lambda 3 is equal to 0. And so the first eigenvalue, -1, is going to be a repeated root. You can see that here, -1 x plus 1 quantity squared. So it's going to be a repeated root. These others are singleton roots. Okay. All right. Then step 3, excuse me. Step 3 is going to be computing the eigenvectors. All right, so we have to, for each of these eigenvalues that we've identified, we have to go back through and calculate the eigenvectors. So calculate the eigenvectors. Right, and we'll do it for lambda 1 equals -1. We'll calculate an eigenvector there. So we want to row reduce. In this case, it's -1, right? So it's lambda. In this case, it's -1. So -1 times the identity minus a, the homogeneous system that has that as its coefficient matrix. Okay, and so what does that mean? Well, you've got -1, 0, 0, 0, 0, -1, 0, 0, 0, 0, 0, -1, 0, 0, 0, -1. This should be a -1, sorry. Like that, okay? So you've got that guy minus a, which is -4, 7, 1, 4, 6, -16, -3, -9, 12, -27, -4, -15, -18, 43, 7, 24. Writing out these arrays. is a little much. Now, when you actually do that subtraction, you get 3, -7, -1, -4. Yes. 0 minus, yep. Okay, I just wrote that wrong. That's okay. And then you get -6 and 15, -3 and -9. I think it should be 3 and 9, actually. And then you get -12 and 27. And then you get 3 and 15. And then 18, -43, -7, and -25. So, yep, -25. Okay. All right, so you get that thing there. All right. So then you have to solve the system based on this, don't you? Okay, and then solve. Basically, just augment this with a 0 column. Okay, and solve this. Right, so solve the system. And when you do that, you can produce an eigenvector x1 and x2. You can produce 2 distinct eigenvectors for this system. So x1 is equal to -2, -1, 1, and 0. And you can get a second eigenvector, which will be -1, -1, 0, and 1. Okay, and these would be the 2 eigenvectors that work with lambda1 equals -1. Okay, and then you have to repeat this process for lambda2 equals, what was lambda2? Lambda2 was 2, and lambda3 equals 0. So you have to repeat this process a couple more times, and there's really no getting around that, but you can get a couple more eigenvectors. x3 equals 1, -2, -4, 6, and that corresponds to lambda2. And you can get an x4 corresponding to lambda3, which is equal to 1, -3, -3, 7. Okay, and so you can get that. All right, so we've got our 4 eigenvectors. So step 4 is to say, okay, do you have enough eigenvectors? If so, proceed, and we do. So we have 4 distinct eigenvectors, so we can proceed. Right, if we could only find 3, then we'd be out of luck, right? But we have 4. All we need is 4. Okay, and so now we can form P. So P is equal to the matrix x1, x2, x3, x4. So these are the columns, and these are obviously the eigenvectors that we just found. So we can plug those in. -2, -1, 1, 0. That's this guy, and then this one, -1, -1, 0, 1. And then 1, -2, -4, 6. And then 1, -3, -3, 7. And so there's our matrix P. Okay, and so then, once we've got our matrix P, we know that P has an inverse because it has 4 distinct eigenvectors. It's full rank. And so P is invertible, and we can just verify that D is equal to P inverse AP. And so in this case, what is our D? Well, if we don't want to find the inverse, we could actually verify this by going P times D equals A times P. Or I can left multiply by P on both sides, and that makes the verification a little easier if you don't want to find that inverse. And so you could verify this. So your P matrix is right here. So -2, -1, 1, 1, -1, -1, -2, -3, 1, 0, -4, -3, 0, 1, 6, 7. Okay, and then your diagonal matrix is just going to be -1, 0, 0, 0, 0, -1, 0, 0, 0, 0, 2, 0, and then 0, 0, 0. Is it 0? Did I write that down right? Was the second eigenvalue? Yeah, 0. Okay, so that's your diagonal matrix. So this is your P, this is your D, and then your A, of course, is just the matrix we started with. So -4, 7, 1, 4, 6, -16, -3, 9, 12, -27, -4, -15, and -18, 43, 7, 24, right? And so that's your A. And then you could write P out again here. I'm out of space, and I think I'll go berserk if I have to write another matrix out. But you'll find that at P times D is going to give you something, and A times P will give you the same thing, which implies that D is indeed equal to P inverse AP. Right? And so you'll see that this works out and is almost magical. Okay? Excellent. Excellent. Very good. And so we haven't actually formally defined a diagonalizable, but let's do it now. An n by n matrix is, well, an n by n matrix A is diagonalizable, right? Diagonalizable if and only if there exists a non-singular n by n matrix P such that D equals P inverse AP is diagonal. Right, so an n by n matrix A is diagonalizable if and only if there exists a non-singular n by n matrix P such that D, calculated from P inverse AP, is diagonal. Okay, very good. Right, and so we're almost done. This feels like an afterthought, but it is important. It does come up later in the course, but I want to point it out. So if you notice in our previous example, we found 3 eigenvalues, but we actually had a characteristic polynomial of degree 4. So our previous example had 3 eigenvalues, but PAX had degree 4. Right, and so this is going to lead us into our next definition. Right, I mean, we kind of talked about this a little bit already with the repeated roots question, but this is going to be the definition of algebraic multiplicity of eigenvalues. So let's let A be an n by n matrix, and let lambda be an eigenvalue for A. Okay. Let's suppose that x minus lambda to the kth power is the highest power. It's the highest power of x minus lambda that divides P of A of x, right? So meaning it's a root, right? It's a root. X minus lambda raised to the k would divide the polynomial, right? But if I went to k plus 1, it wouldn't, right? That's the idea, right? Basically, the idea is you've gathered all of those together. Okay. So in this case, you know, where you've got x minus lambda to the k is the highest power of x minus lambda that divides the characteristic polynomial, then k is called the algebraic multiplicity called the algebraic multiplicity of lambda. Okay, and this will come up later in the course when we start to identify the value and the usefulness of some of this diagonalization stuff. This algebraic multiplicity will come up. So just a quick example, just to make sure this is clear, like what we're doing here. Previously, we had a characteristic polynomial that was equal to x times x minus 2 times x plus 1 squared. Right? So we had this characteristic polynomial, and so we said that we have lambda 1 equals -1, lambda 2 equals 2, and lambda 3 equals 0. What is the algebraic multiplicity of each of these? Right? In this case, it's 2. In this case, it's 1. And in this case, it's 1. Right? And you can just kind of read those off of the characteristic polynomial, especially if you've got it factored down like this. Right now, so this obviously is a very this is a concept closely aligned with the idea of repeated roots of polynomials. Right? Except for the fact that it's used in in an additional context, you might say this is the same idea, but it does have additional uses that don't really come up when we're talking just about repeated roots from algebra. Okay, all right, so that's where we're going to leave it here. This has been a very long section, but coming up, we're going to shift gears a little bit and talk about finite dimensional vector spaces next. And so we'll get into a slightly longer collection of sections where we'll get into kind of a difference. Up until now, it's all been about how to calculate things with matrices. Now we're going to shift into some of the more abstract properties of linear algebra, things like vector spaces, subspaces, etc. And so that'll be an interesting change. But we'll certainly come back to diagonalization later. We'll have some additional use cases that'll come up. Okay, I think that's a good place to leave it. So take care, everyone, and we'll talk to you all later.